I am going to be solving question number 42 from the night textbook. This question says, the 70 kilogram student in the figure balances a 1200 kilogram elephant on a hydraulic lift. What is the diameter of the piston the student is standing on? So as you can see here, I've drawn the student on one side, the elephant on the other, as well as we know the diameter of the piston that the elephant is standing on, which is 2 meters. And we know that this hydraulic lift has oil. So the way that a hydraulic lift works is based on Pascal's law, according to which the pressure difference on the same level is 0 when the fluid is at rest. So as you can see, the elephant and the student are at the same level. Therefore, P1 is going to be equal to P2. We can then define this further, saying that P1 is equal to F1 over A1. Therefore, P2 is going to be equal to F2 over A2. So what we want to find is A1, which is going to be the diameter of the piston that the student is standing on. In order to get this, we're going to have to rearrange the equation, but first we want to define A1 as pi r squared. We're using pi r squared because the piston is round, so this is just the equation of a circle. So then we can rewrite the equation as F1 over pi r squared is equal to F2 over pi r squared. And then after a bit of rearranging, we can get r is equal to the square root of F1 over F2 times r. And then from there, we'll just plug in our values of 70 kilograms for F1, 1200 kilograms for F2, square root times the radius of the piston that the elephant is standing on, which is going to be half of the diameter. So that's just 1 meter. And then we get 0.242 meters. So this is going to be the diameter of this piston. For part B, this question asks, when a second student joins the first, the piston sinks 35 centimeters. What is the second student's mass? So we're adding a student on this side, and we don't know his mass, but we know that this sinks 35 centimeters. Therefore, the elephant must go up 35 centimeters, because when force is pushed down here, it will be pushed up here. So we're going to use a very similar equation to the first part. F1 over A1 is equal to F2 over A2. But we're going to have to subtract hydrostatic pressure from this side of the equation due to the fact that the pistons are moving. So we're going to subtract PGH, which is just the formula for hydrostatic pressure. It can be defined as pressure, acceleration due to gravity, and height. So first, we're going to add our 70 kilograms to here. So we have F2, which is the mass of the second student, plus 70 kilograms. And this is all multiplied by the gravitational constant over A2 minus PGH. So as you can see here, the G's are going to cancel out. And we're going to move this to this side because we want to get F2 by itself. And from here, we're just going to keep rearranging the equation until we can get F2 by himself. So we'll multiply A2 to this side. And then from here, we will subtract 70 kilograms to the side. Okay, so now that we have F2 all by himself, we can plug in the numbers and solve this equation to get the mass of the second student. So F2 is equal to F1, which is the mass of the elephant, over A1, which we have already discovered is pi r, which is 1, squared, plus pressure. The pressure exerted by oil is a constant which can be found in the textbook, and it's 900 kilograms per meter cubed, times H, which was 35 centimeters, which the piston sunk. So we convert that to meters. A2 is what we solved in the last part, which is 0.242 meters squared pi, and then minus 70 kilograms. You punch this into your calculator and your end result is 58 kilograms. So the second student added to the side of the piston weighed 58 kilograms.